Okay, so we're going to look at creating Huffman trees. So this is a technique you want to be able to employ, which is an example of how to do lossless compression on text. So we'll stick with this because it's an example from one of the exam boards. So consider the sentence, he ties the tether. So the frequency of each character, including the space, is down here in this table. So you see E as a character appears the most, T the next, then H and space together, and then S, R, and I only appear once in this above sentence. So you need to know all the different characters you've got in what you're encoding and the frequency at which they occur, the amount of times you see them. Once you know that, we need to create a node, which we'll describe as these round edge rectangles here. Create a node for each of the different characters. And we're going to label each node with a frequency of the character as well as the character itself, which is in brackets. So we've got I appears once, T appears 4 times, etc. So arrange them in order of frequency from lowest to highest. You'll understand why as we go through. So that's step one. Once you've done that, we then need to follow this algorithm through multiple times. So it's sort of recursive, but don't worry about recursion just yet if you're not sure what that means. So we take the top 2 nodes out. So if I just go back, you can see the top 2 nodes were I and R. So what I'm doing is I'm taking those top 2 nodes out and I'm creating a new node, which is the amounts added together. So 1 plus 1 is 2. So we've got a new node now, which is branches to the 2 previous nodes. Okay, and we label that with the value. We then have to put that in the position of in the order. So obviously if that equaled 7, it will be down at the bottom. So we take the top 2 nodes out, create a new node and link them. And the new node is the value of them added together. And we put it in its correct position. And then we do the exact same thing again. But obviously our top 2 nodes now are these 2. So we took those 2 out. 2 plus 1 is 3. 3 is still in the top position of this. And we're creating a tree. Okay, so sorry, just go back. So then we take the top 2 again, 3 plus 3. We branch them to a new node called 6, and 6 gets pushed to the bottom. It's quite a big number now. Okay, and then we'll go again. So now we're going to take 3 and 4. So take 3 and 4, link them together, which equals 7. 7 gets moved to the bottom, and it now looks like we've almost got 2 sort of trees going on. But they'll all link together in the end. So now we're taking the top 2, which is 5 and 6 here. So we take 5 and 6, add it together as 11, put it to the bottom. So now we've only got 2 in. And because we've only got 2 in, we take them, link them together, and add them together. It's 18. And now we can do a really simple error detection because 18, there should be 18 characters we're encoding. If that number matches the total amount of characters in the thing that you are creating the Huffman tree for, then you've probably done it right. If there's any other number, you've probably done it wrong. Now, you can all probably make a tree like that, but now you still don't really understand why we're doing it. So the idea is now that you label the branches, okay? So what we do is we label the branches and the different codes are going to represent how to get to different letters. And the shortest code will be the most frequently used letters. So for example, if I wanted to put a code in for E that I could store in the computer, E would be 0, 1. So to get to the letter E, I just have to put 0, 1. So 2 bits of data will get me to the letter E. To get to letter H, I need 1, 1. To get to T is 1, 0. To get to R, it's 0, 0, 1, 0, 0. So can you see the letters that are used the least have the longest encoding numbers. So here you can see them all in a table. Now, the really clever thing about this is, although the codes for each character vary in length, they're all known as prefix codes. What that means is that they're assigned in a way that the code for one character is not the starting code of another. So you can see, for example, here, space is 000. There is no other code that starts 000. So basically, you couldn't misinterpret any of these codes as anything other than what they are. So E is 01. There's no other code that starts 01. T is 10, nothing else. H is 11, nothing else. And the Huffman tree does that for you automatically. So what we could do then is we could, I can't remember what our sentence was, but we could encode our letters using these. And instead of using, say, 7 bits of data per letter, if we're using the basic ASCII character set, this would be a lot more, because the more frequent letters are only using a few bits each. Okay, so that's one example of a lossless compression technique, and it's called Huffman trees.